Assalamualaikum warahmatullahi wabarakatuh. Welcome to part 5 of welding. So today we are going to cover oxy-fuel gas welding and electron beam welding in the first part of the welding part 3, and the second part will be the solid state process. Oxy-fuel gas welding is in a group of fusion welding. So in this process there will be several type of gases involved, where the gases will be burned with the mix of the oxygen. So this gas is used for flame cutting torch, in whether to cut and separate metal plate or to conduct the oxyacetylene welding. In this process, the fusion welding is performed by the combustion of the acetylene and also the oxygen. So the flame will be directed to the by a weld torch, and then filler metal will added. So composition of the filler must be similar to the base metal, and the filler rod also often coated with the flux to clean the surface and also to prevent the oxidation. Now let us see the schematic diagram for the oxyacetylene welding. So if you can see here, there will be a torch over here. So in this torch, there will be mixture of acetylene gas and also oxygen coming in, and then there will be combustion over here, and usually filler rod will be together with this process. Okay, so then the combustion happen over here, where the filler will be melted and then added to the molten weld metal. Okay, so in this area, not only the filler metal will be there, the molten metal also include the base metal. Okay, so meaning because it is a fusion, right? So the base metal must be melted. Let us look into the process like in the picture below. Okay, so if you can see, there are combustion of the filler and also the base metal happen on the red area over here. So that's how the oxyacetylene welding process take place. Here is the oxyacetylene torch. So there are three levels of gas combustion over here. So if you can see, there are outer envelope where the temperature is the lowest, which is around 1260 degrees Celsius. So on this outer envelope, this outer layer spread out and shield work surface from the atmosphere, and then the middle one is acetylene feather. It's around 2090 degrees Celsius, and the last one will be inner cone, which is around 3480 degrees Celsius. So neutral flame of the oxyacetylene torch indicating temperature achieved is like the one that presented in this picture. So in this oxyacetylene welding process, acetylene is the most popular among the welding type in this group, because it's capable of achieving high temperature, which is around 3480 degrees Celsius. So in this process of welding, there will be two stages of reaction of acetylene and oxygen. The first stage will refer to the inner cone of the flame, where acetylene will react with the oxygen. Okay, and then we'll create the carbon dioxide, hydrogen, and also heat. So this heat is used for the welding process. So this inner cone will be in bright white color. So the second stage of reaction, which is in the outer envelope, so this one, the carbon dioxide and also the H2 will react with additional oxygen here. So and then it will create carbon dioxide and also water, H2O, in term of steam. Okay, and heat. Okay, so this is the outer envelope, which is almost invisible blue and orange color. Total heat that can be generated by the acetylene in this combustion, two stage of combustion, will be around 55 times 10 of power 6 joule per meter cube. Okay, so however, because of the temperature distribution in the flame, the way in which the flame spread over the work surface and will be not so much, and a lot of losses will go to the air. Okay, power density and also heat transfer in oxyacetylene welding are relatively around 0.1 to 0.3 only. Okay, so another problem that related to the oxyacetylene welding will be acetylene and oxygen is very highly flammable, so it's quite dangerous for those who are the beginner in the oxyacetylene welding. So apart from that, C2H2, which is the acetylene, is colorless and odorless. Okay, so if you consume this and smell the gas, you might faint. Okay, so because you don't know there is no color and also there is no odor. Okay, so due to that, the manufacturer process the acetylene into garlic odor. Okay, to they give the garlic odor to the gas so that people will know that if there is any leakage or anything. Okay, so if there we don't know the color and we don't also smell anything, so if there is any spark of fire, they might going to start the big fire, right? So that's why they process it into the garlic odor. Apart from that, acetylene also physically unstable at pressure above 15 lb, or around 1 atm. So that's why the storage cylinder will be packed with the porous filler material saturated with the acetone. So acetone will dissolve about 25 times its own volume of acetylene. So this one can cause intoxication if we inhale the smell. Okay, so different screw thread also used for the acetylene and oxygen, so that it will be easier to identify which one is acetylene and which one is the oxygen, so that to avoid any accidental connection of the wrong gases. Apart from the acetylene, there are some other alternative gases also that can be used for oxy-fuel gas welding. So if you can see the list, it will be acetylene, which is around 3000 plus temperature can be achieved. Apart from that, there are also MAPP. MAPP is the methyl acetylene propadiene. Okay, so this one is around 2927 degrees Celsius. You can also use hydrogen, propylene, propane, and also natural gas as the substitute for the acetylene. So let us see some problem on this oxyacetylene process. So an oxyacetylene torch supplies 0.3 meter cube of acetylene per hour and an equal volume rate of the oxygen for oxyacetylene welding operation on 4.5 mm thick steel. Heat generated by combustion is transferred to the work surface with heat transfer factor F1 equal to 0.2. If 75% of the heat from the flame is concentrated in circular area of the work surface, that is 9.0 mm in diameter, find A. Rate of heat liberated during combustion, B. Rate of heat transfer to the work surface, and C will be average power density in the circular area. Okay, so let's see the solution for this one. Now, let us see the A, which how much is the heat liberated. Okay, so since it's given that the gas is supplied 0.3 meter cube per hour, right? So if you can remember previously, the value for the acetylene after the combustion, it will be around 55 times 10 of power of 6, right? So what you have to do is you just calculate with this 1, okay, 0.3. So then you will get the rate of the heat generated, which is 16.5 times power of 10 of power of 6 joule per hour. So if you change per second, then you will be around 4583 joule per second. Okay, so the second one is how much is the heat transfer. Okay, so since the F1 is given 0.2, so what you have to do is just F1 times the RH, then you will get 0.2 times the 4583, so you get around 917 joule per second only heat will be received by the work surface. So the last one, the area of the circle in which 75% of the heat of the flame is concentrated. So you have to calculate the area first. So A equal to pi d naught over 4. Okay, pi d squared over 4. Sorry. So there will be, the area will be 63.6 mm squared. So then if you remember the equation for the power density, P over A, right? So P is equal to 0.75 because why? 75% of the heat is concentrated in this area times the 917 joule per second, which is the rate of the heat received by the work surface, and then divide by the area. So then you will get the power density is around 10.8 watt per mm cube, no, mm squared, sorry. So let us look into the the last part of the fusion welding, which is electron beam welding, or we call as EBW. So for EBW, the fusion welding process, which heat for welding is provided by high focus, high intensity stream of electron striking work surface. Okay, so previously it is using the combustion of the gas, right? For the OC fuel gas welding, but for this one it is generated by the electron that strike on the work surface. So in this process, the electron gun will be operating at high voltage, which is around 10 to 150 kilovolt typically, to accelerate the electron, and then the beam current will be in milliamp measurement. Okay, so power in EBW not exceptional, but power density is very high. So in term for this one, compared to the oxy acetylene, this one power density is very high. Okay, so it focus on the area, and then not much of the heat is going out to the surface. Okay, most of the energy is gone to the work surface. Okay. Okay, electron beam welding usually perform in the vacuum chamber, so that's why there will be less heat generated to the environment. So in this process, there will be a pump over here where the electron beam will be generated in the filament. So this one, everything is the same. This just want to show you the example. In this area, so for example, here there will be electron beam column where the electron will be generated. So everything will be focused on this one. There will be stigmators, focus coil, and also deflection coil, in order to focus the electron to go directly to the work surface that we want to work on. Okay, so then when the electron go to the surface here, then welding can be performed. Okay, so this the bottom one will be the vacuum chamber for the part. Okay, and the workpiece also will be in this area. Okay, when EBW first developed, it has to be carried out in vacuum chamber to minimize the disruption of the electron beam by the air molecule. So this one is very inconvenient production, and also the pump time also will take a long time, which is around an hour. Pump down is to make the area vacuum. But now the vacuum level is separated into three level, which is high vacuum welding, medium vacuum welding, and also non-vacuum welding. So for high vacuum welding, this one is when you want to create a very high quality of weld. Okay, for medium welding, welding is separate chamber, but partial vacuum reduce the pump down time, but then the quality might be lower compared to the high vacuum welding. And the last one is non-vacuum welding, where the welding done at one or near atmospheric pressure, where the work position close to the electron beam generator, so that not so that the focus will be better, since there is no vacuum environment anymore, right? So this one will require the vacuum divider to separate work from the beam generator. So for EBW, there are advantages and disadvantages. As for the advantages, you can produce a very high quality welding, which is a deep and narrow profile, where you can focus on the area, and then there will be less damage on the area. So there will be limited heat affected zone and low thermal distortion, because the process will be very focused. So, and there will be no flux or shielding gases needed in this process. So for the disadvantages, the equipment will be very costly, and then precise joint preparation and alignment is required. If not, then because the contact area is very small, so if the joint preparation is not aligned together properly, you might weld on the different places instead of the place that you want to join. Okay, and then of course vacuum chamber is required, and also safety concern will be EBW can generate X-ray, so that one is can be dangerous to the one that handle the machine. So here is the example of the machine for the electron beam welding. Okay, so let us look into the problem for the EBW. So the voltage in EBW is 45 kV, current is 50 milliamp, focus on a circular area is 0.25 mm diameter, heat transfer factor F1 equal to 0.87, and calculate the average power density in the area in watt per mm squared. So now let's see the solution. So for solution, in order to calculate the power density, it is equal F1 EI over A, because the power is generated by the current and also the voltage, right? So then first you calculate the power, P equal to F1 EI. Okay, so it's 0.87 times the 45 kV times the 50 milliamp. So you'll get the power is 1957 watt. Area A equal to pi d squared over 4. Then when you calculate, it will become 0.0491 mm squared. So then PD will be 1957 divided by 0.0491, so you'll get around 39.8 kilowatt per mm squared. So let's see the second one. An electron beam welding operation is accomplished to butt weld two sheet metal parts that are 3 mm thick. Unit energy melting equal to 5.0 joule per mm cube. The weld joint is 0.3 mm wide, so that the cross section of the fused metal equal to 0.35 mm by 3.0 mm. If accelerating voltage is 25 kV, current 30 milliamp, heat transfer factor F1 is 0.85, melting temperature 0.75. Determine the travel speed at which this weld is made along the seam. So if we look into the equations that previously we see, the equation that have the V value will be in the RHW. Okay, so RHW equal to F1 F2 EI equal to UM AV, right? So now, since they want the travel speed, so you have to arrange the equation into V equal to F1 F2 E1 over AW. Okay, so you just rearrange this equation and you will get this equation. Okay, so then Now you will see what are the things that still don't you don't have in this equation. F1, F2 is given, E is given, I is also given, also given. Only value that not given is A, right? So you have to calculate the value A. So 0.35 times the 3.0 here, okay, and then you will get 1.05 mm squared. So then you just put all the value inside the equation and you will get the travel speed is around 91.05 mm per second. That's the end for welding part 5. See you in part 6.